So welcome everyone to this week's Durham Geometry and Topology seminar. So it's a pleasure to have Csaba Nagy from DATH, but currently in Melbourne. So he's going to talk about the Sullivan-conjecture in complex dimension 4. Thank you.
Thank you, and thank you for the opportunity to give a talk here. So what I'm going to talk about is joint work with Diarmuid Crowley. And this is the Sullivan conjecture about the classification of complete intersections in dimension 4. So in the first part of the talk, I will give an introduction to complete intersection, their definition and some basic properties. Then I will state the Sullivan conjecture and give some motivation and known results about it. And finally, I'll say something about the proof of the Sullivan conjecture in dimension 4. So first, we are considering complex projective complete intersections. So an n-dimensional complete intersection is defined as the transverse intersection of k hypersurfaces in CPM plus k or some k. This means that a complete intersection is always a smooth manifold. In fact, it's a smooth projective variety. And the hypersurfaces that determine the complete intersection are algebraic hypersurfaces, so they are defined by homogeneous polynomials. And so if we denote by d1, d2, and some dk the degrees of these hypersurfaces, then we will call the multi-degree of the complete intersection the collection of all these degrees, and the total degree of the complete intersection is the product of the degrees. And the simplest examples of complete intersections are the non-singular hypersurfaces, which are just defined by one homogeneous polynomial. Here we see an example degree 4 equation, which defines a K3 surface in CP3. Maybe also give a counterexample. So if we again take CP3 and these three equations, then the set of roots of these equations is diffeomorphic to CP1, which means that it has a codimension 2. But since it's defined by 3 equations, these hypersurfaces cannot be transversed to each other. So this is not a complete intersection, even though it's still a smooth variety. So the first result about the classification of complete intersections is the theorem of Thom, which says that the diffeomorphism class of complete intersection only depends on its multi-degree and not the actual polynomials. And this is because if we take the space of all tuples of polynomials with a fixed degree which define a complete intersection, then this space is connected. So in fact, we get that any two complete intersections with the same multi-degree are deformation equivalent, which basically means that their complex structures are in the same component of the modular space complex structures of the underlying smooth manifold. And this theorem allows us to introduce this notation x and b for an n-dimensional complete intersection with a fixed multi-degree D. So this is a smooth manifold which is well defined up to diffeomorphism. So the simplest example for the use of this notation is if we just take a, if the multi-degree is 1, then we just take a linear subspace in CPN plus 1, so we get CPN. In dimension 1, a complete intersection is of course an oriented surface, and we can compute its genus from the degrees, which is given by this formula. And in dimension 2, there are some interesting examples. For example, the K3 surfaces can be obtained in 3 different ways with the multi-degrees 4, 3, 2, and 2, 2, 2. Yeah, so next we want to compute some.
Can you just go back to the previous slide and remind me of the notation again? I'm sort of. So what is the? Just remind me what the 1s and what the Ds mean.
So in the second example, x1 means that it has dimension 1, the complete intersection, and the Ds are the degrees of the hypersurfaces. So this is a subset of CP k plus 1, which is defined by the intersection of k hypersurfaces.
So it's in CP k plus 1?
Yes.
What the sum of?
Sorry?
So it's a subset of CP k plus 1.
Correct.
Okay.
So we have k hypersurfaces given by these degrees d1 and so on dk, and they intersect each other transversely. So each of them decreases the dimension by 1.
So a hypersurface means just something that's determined by a homogeneous polynomial?
Yes.
Okay, isn't it? Right. Okay, so it's more complicated than just like a. It's fine.
Sorry,
that's all. But now I do.
Okay.
Complete.
Then I will move on to the determining the basic invariants of complete intersections. And so first of all, we want to know the cohomology groups and the cohomology ring complete intersection. So first we consider this the natural inclusion of a complete intersection into some CP n plus k, and it follows on the Lefschetz hyperplane theorem that this inclusion is n-connected, which means that it induces an isomorphism on the homotopy groups up to dimension n-1 and the surjective number in dimension n. And this means that first of all, if the dimension is at least 2, then the x and d has the same fundamental group as the projective space, so it's trivial. And we also get that below the middle dimension, it has the same cohomology groups as the complex contractive space. So in even dimensions it's z, and in odd dimensions it's 0. And by point regularity, the same holds above the middle dimension, and in dimension n it has to be some free number. In fact, we know something about the ring structure too. If we denote by y the generator of the cohomology ring of CPN plus k, then we can define its pullback denoted by x. And below the middle dimension, the powers of x will generate the cohomology groups of the complete intersection, just like the powers of y generate the cohomology groups of the projective space. And in the top dimension, the top power of x is equal to b times the generator of the cohomology group. This basically follows from the fact that a degree di hypersurface represents the Poynter radius of di times y. So the intersection of these hypersurfaces will represent the dual of d times the appropriate power of y. And an important consequence of this fact is that the total degree is the homotopy invariant of a complete intersection. We can read it off the cohomology ring, at least if the dimension is at least.
So D is the product of the DIs?
Yes.
Yeah.
The total degree is the product. Okay. Next, we will consider the stable normal bundle of a complete intersection. So first, we introduce notation. We will denote by H the conjugate of the topological bundle over CPM plus K. And then it's known that the stable normal bundle of the projective space is the inverse of n plus k plus 1 times H, and the normal bundle of a degree di hypersurface is the di's tensor power of H, or precisely its intersection. So because of this, we can determine the stable normal bundle of a complete intersection, which is just the Whitney sum of the stable normal bundles of the projective space and the normal bundles of the hypersurfaces. And this allows us to compute the Chern-classes and Pontryagin-classes of the complete intersection, which are given by these formulas. And so the important feature of this formula is that every Chern-class and Pontryagin-class can be given as a multiple of the appropriate power of x, and the coefficient can be computed from the degrees and the dimension. Okay, so let's return to the question of the classification of complete intersections. So we saw that if two complete intersections have the same multi-degree, that they are diffeomorphic, but the converse is false. So we already see examples in dimension 1 and 2. In particular, in dimension 2, we saw that the K3 surface, which is well-defined up to diffeomorphism, can be obtained from 3 different multi-degrees. There are also examples in higher dimensions. For example, in dimension 3, this example was given by Littmacher and Wood, and we found an example in dimension 4 using a proof of the Sullivan-conjecture. So in this example, the notation means that we have, for example, in the first complete intersection, 150 copies of series. So these complete intersections have very high codimension. And another important result of the Governing rule is that if two complete intersections are not just diffeomorphic but deformation equivalent, then they necessarily have the same multiple. And this result is very useful now, because if we can find more examples of diffeomorphic complete intersections with different multi-degrees, then we know that they are not deformation equivalent. So their complex structures have to lie in different components of the moduli space of complex structure of the underlying smooth manifold. So using this result and the Sullivan-conjecture, we can construct examples of smooth manifold with non-connected moduli space. Okay, so now let's go on to the statement of the Sullivan-conjecture. So if we have n-dimensional complete intersections, where the dimension is at least 3, then the conjecture claims that they are diffeomorphic if and only if they have the same invariants, where the relevant invariants are the total degree, the Pontryagin-classes, and the Euler-characteristic. So first, note that it makes sense to compare the Pontryagin-classes of different complete intersections, because we saw that they are always multiples of powers of x, and so we can just compare the coefficients. And it's also easy to see that these conditions are necessary. So we saw earlier that the total degree is in fact not just a diffeomorphism invariant, but actually a homotopy invariant, and the same is true for the Euler-characteristic, and of course that Pontryagin-classes are diffeomorphism invariants. So next, I'll mention some known results about the Sullivan-conjecture. So in dimension 3, the simply connected 6 manifolds are classified by Hall and Jupe, and the Sullivan-conjecture follows from their classification result. In dimensions between 4 and 7, it follows from the work of Fang and Klaus and Thom and Wang that the conjecture holds up to homomorphism instead of diffeomorphism. In fact, in dimension 4, the statement is a bit stronger, because the conjecture holds up to connected sum with a homotopy sphere. And it's worth mentioning a new result of Diarmuid, who computed the alpha invariants of complete intersections in dimension 4k plus 1, and proved that they have the, if two complete intersections have the same invariants, and then they also have the same alpha invariant. So this is consistent with the statement of the conjecture.
I'm slightly confused about the invariant, the homomorphism versus diffeomorphism thing. I mean, all the invariants that you said are homomorphism invariants, right? I mean, you fix the total degree, and then the Pontryagin-classes are famously homomorphism.
Yeah.
So I'm just confused about the logic, I guess. So,
yeah. So I think you're thinking about the converse of the conjecture. So if two complete intersections are homeomorphic, then of course they have the same invariance.
Yes.
But if they have the same invariance, then as far as we know, they don't necessarily have to be homeomorphic.
They don't have to be homeomorphic.
No, in general, no. Well, in these dimensions, yes, because it was proven. But in high dimensions, we don't know.
I'm just confused. Like you have this, you have the exotic 8 sphere.
Yes.
And you add that on. Are you saying that is it like that? If the conjecture holds, does that mean that only one of those two manifolds that you get from either is a complete intersection?
If the conjecture holds up to diffeomorphism, yes.
Yeah. So you have a complete intersection. You add on the exotic 8 sphere, and you don't have a complete intersection anymore. If the conjecture holds.
Well, that's one of the ways that the conjecture can hold. Yes.
Okay.
But the other, it can happen that if you add the exotic sphere, then you get the same manifold.
You just get the same manifold. I see. Yeah. Okay.
But I'll talk a bit about this. Yeah.
Great. Yeah. Yes.
So there's one more general result that I wanted to mention, like Kreck and Traving. They proved that the Sullivan-conjecture holds in any dimension under the condition that the total degree is divisible by a sufficiently high power of primes below roughly square root of n. In dimension 4, this condition says that the total degree must be divisible by 2 to the 6. And our main result is that the Sullivan-conjecture holds in dimension 4 up to diffeomorphism without any further assumptions. The total degree. Okay. So let me just recall the definition of the homotopy spheres first, because it will play an important role in the proof. So in general, we denote by theta n a group of homotopy n spheres, which are manifolds that are homomorphic but not necessarily diffeomorphic to Sn. And these form a group under the connected sum. And the classical result from surgery theory by Kepler and Milner is that this group is closely related to the Cocker-Naughton J homomorphism, and in dimension 4K they are actually isomorphic. So this allows us to compute the groups of homotopy spheres in low dimensions. In particular, for us, the relevant group is theta 8, which is isomorphic to Z2, and so there is a unique exotic 8 sphere which we will denote by sigma. Okay. So there was this result by Fang and Klaus that I mentioned earlier, that the conjecture holds up to connected sum homotopy sphere, which means that now the conjecture can fail only if we have two complete intersections x and y, such that one of them is diffeomorphic to the other plus sigma, but they are not diffeomorphic to each other. Which means that to exclude this possibility, we need to prove that for every complete intersection, either x is diffeomorphic to x plus sigma. If this is the case, then we will say that x is real. Or the other option is that if x is not diffeomorphic to x plus sigma, then we have to prove that x plus sigma is not a complete intersection. So hopefully this answers your question. bit more detailed way. Okay. And our proof is a case-by-case argument. So in the first case, we will consider spin complete intersections, and we will show that they are flexible. In the non-spin case, will be divided further into two cases, depending on whether the Stiefel-Whitney-class W4 is 0 or not. If it's non-zero, then that's the second case we consider. And we will show that these complete intersections are rigid. And the remaining case, when W4 is 0, is again divided into two subcases. One of the subcases is when the total degree is odd. This is the third case that we consider. And in the other case, the total degree has to be divisible by 16. And this case follows from an improvement of the result of Kreck and Traving that I mentioned earlier, so I won't talk about that. Okay. So first, I'd like to talk about the flexible cases in general. So this, we can think of this in general as the more difficult case, and there are many flexible complete intersections. For example, the simplest one, CP4 itself, is flexible. This follows the result of a cylinder. And so in this case, we want to show that x plus sigma is not diffeomorphic to any complete intersection. And the general idea for doing this is that we want to find a special property that complete intersections have, but x plus sigma doesn't. And of course, these are smooth projective varieties, so they are Kähler manifolds. So this would be a candidate property that we could use for the proof if we could prove that x plus sigma is not Kähler. Unfortunately, this is a very difficult question, and in general, the answer is unknown. So we have to find different properties. Okay, so now I'm moving on to the first case of spin complete intersections, and for this case we will use a special property of complete intersections, namely if we have complete intersection x, then we take the complex line bundle over it with first Chern class x. This line bundle is uniquely determined, and if we take the sphere bundle, this line bundle, then we prove that this this sphere bundle always has a framing such that it's framed in orthogonal. And this, we will show that this is a special property of complete intersections. So to prove this, we first start with xn plus 1 p. So this is the complete intersection in Cp n plus k plus 1, which is defined by the same degrees. And from this, we can obtain xnd by intersecting it with Cpn plus k, so a linear subspace. And so this construction is what we will use. First, we should remember what we saw earlier in the talk, that the stable normal bundle of the complete intersection X and D is the pullback of a certain bundle over Cpn plus k, which we could express in terms of H. It doesn't matter what the exact formula is. All we're using it now is that it's a bundle over Cpn plus k or Cpn plus k plus 1. In this case, what we have is that Xn is the intersection of Cpn plus k and Xn plus 1. This means that the complement Xn plus 1 minus Xn is embedded in Cpn plus k plus 1 minus Cpn plus k. And this is just a contractible space, an open cell of dimension 2m plus k plus 1. Which means that any bundle over it is trivial. And as the stable normal bundle of this complement is the pullback of this stable bundle over this contractible space, it has to be trivial too. And so this is how we see that the complement of Xn in Xn plus 1 is a stable parallelizable manifold. On the other hand, we also see that the normal bundle of Xn in Xn plus 1 is the pullback of the normal bundle of Cpn plus k in Cpn plus k plus 1. And that bundle is H, which has first Chern class Y, so its pullback has first Chern class X. So this normal bundle is exactly that bundle that we considered in the statement. So if we take a tubular neighborhood of Xn in Xn plus 1, and we take the boundary of this tubular neighborhood, that's exactly this S1 bundle that we are considering. And now we see that this S1 bundle is also the boundary of the complement Xn plus 1 minus Xn, which is stable parallelizable. This means that it's framed non-covariant in the restriction, the framing of the complement.
Wait, are you saying that this boundary is actually a sphere of dimension, whatever some dimension?
It's not a sphere; it's a sphere bundle.
But well, I thought it was the boundary of the top cell. Maybe I didn't follow the argument.
It's well.
You said that complement Xn plus 1 minus Xn is the top cell of Cp.
It embeds in the top cell.
It embeds in the top cell. Okay.
So yes, we can think of this S1 bundle as being embedded in the boundary of that sort of cell.
Okay.
And so we saw that complete intersections have this special property. So now we need to prove that if X4D is a spin complete intersection, and then X plus sigma doesn't have this property, so that if we take the S1 bundle with first Chern class X over this manifold, then it won't be frame non-covariant. And I'll just give a sketch of the proof. So when we add the homotopy sphere sigma, then the frame cobordism class of the S1 bundle over changes by the cobordism class of sigma times S1 with some framing. And it turns out that the cobordism class really only depends on the framing of the circle. And these framings are in bijection, or they are detected by the second Stiefel-Whitney class. So this is how the spin condition comes into play. And in fact, we find that if the complete intersection is spin, then sigma times S1 is not frame non-cobordant with the relevant framing. So this means that this S1 bundle over X plus sigma is not framed cobordant, framed non-cobordant with one framing. And so the last step of the proof is that if we change the framing, then it remains non-zero in the framed cobordism group. So to sum up, we have proved that the complete intersections have a special property determined by these S1 bundles, and if we have a spin complete intersections, then X plus sigma doesn't have this property. So we get, first of all, that X plus sigma cannot be diffeomorphic to X. This is how we see that this case is flexible. And in fact, we see that the X plus sigma is not diffeomorphic to any complete intersection, which proves that the Sullivan-conjecture holds for still complete intersections in dimension 4. Okay. In the remaining cases,
wait, can you just explain that a little bit more? So what's omega 9 framed? And how do I know that this thing is that omega 8 cross S1 is sigma 8 cross, sorry, so omega 9 framed is the stable 9 stem. What's that?
So that's Z2 cubed, I think.
Z2 what?
Z2 cubed, if I'm not mistaken.
Cubed.
And so in fact, we can prove that this is that this element is non-zero in the co-kernel of the J homomorphism.
So the sigma 8 obviously is, and you're saying if you cross with S1 and put the non-trivial framing on the S1, then that's still a non-trivial element.
Yes. So that's the statement, and it's, well, it's a statement about the multiplication.
I guess I don't understand the last line. So the framed cobordism class of the S1 bundle remains non-zero. I mean, if the S1 has the trivial framing on it, then it's obviously null Borden, isn't it?
But we cannot change the framing of the S1, so that's determined by the Stiefel-Whitney class. So so there are two things that we consider here. We have the entire S1 bundle over X plus sigma.
Oh, I see. Yeah, and then there's the thing that's happening on the exotic 8 sphere.
Yes. And so in the last step, we consider the bundle over X plus sigma, because that's what the statement is about. And so in the first 4 steps, we prove that this has one framing with which it is not non-cobordant. And in the last step, we prove that this is actually true for every other framing, because the framings can only be changed on the 9th cell. So the possible elements form a coset of the image of the J homomorphism. And it's not the zero coset.
Okay, cool. Thanks.
I will just talk very briefly about the non-spin cases. In these cases, we use Kreck's modified surgery theory to prove the theorem. So, in general, the setup for this theorem is that we have two manifolds M0 and M1 of dimension 2q and the cobordism between them, together with a fixed base space B with a stable bundle over it, and the normal map from W to B, which is just a continuous map covered by a bundle map from the stable normal bundle of W to the fixed bundle over B. And we have two assumptions. First is that the manifolds have the same Euler-characteristic, and the second is that the maps, the restrictions of this map to the two manifolds M0 and M1 are Q-connected. So basically, we have a normal cobordism between M0 and M1 over B, which satisfies some conditions. And in this case, Kreck defines an obstruction associated to this normal cobordism, and this obstruction has a certain property called elementary if and only if the cobordism can be replaced by an H-cobordism, which means in high dimensions that the two manifolds are diffeomorphic. And usually when one of the manifolds is a complete intersection, then it immediately follows that the obstruction will be elementary. So if we want to use this method to prove that a complete intersection is diffeomorphic to another manifold, then the difficult part of the proof will be finding a cobordism, normal cobordism, between the complete intersection and the other manifold. Okay. So in the second case, which is the non-spin case with non-zero Stiefel-Witten-Klaus W4, we will prove that these complete intersections are rigid, so that X is diffeomorphic to X plus sigma. And so we apply modified surgery where in the setting where the two manifolds at the end are X and X plus sigma. And as I said earlier, what we need to check is that these two manifolds are normally borrowed over an appropriate base space. And of course, their normal Bordism classes differ by the normal Bordism class of the exotic H sphere. So this normal Bordism class is given by a homomorphism from the group theta 8 to the Bordism group of CP infinity with appropriate decorations. And the main part of the proof in this case is showing that this homomorphism is trivial, and hence the two manifolds are cobordism, and hence they are diffeomorphic. And the idea for this is that we define a group theta 8 S21. We start by defining a manifold T, which is just non-trivial D6 bundle over S2. This is unique because such bundles are classified by max to BSO and Python of BSO is set to. And then we take the group of diffeomorphisms of the boundary of T after isotopy. And this group can be computed, it's isomorphic to Z4. And the reason it's relevant in this case is that T can be regarded as the neighborhood of the two sphere in a non-spin complete intersection. So this means that if we have a diffeomorphism of boundary T, then we can cut out T from the complete intersection and reglue it with a different diffeomorphism of the boundary. And this way we get an action of this group theta 8 S21 on the at the end of the day on the cohomology class of the complete intersection. And which is again given by a homomorphism from this group theta 8 S21 to the Bordism group of Cp infinity. And in fact, what we get is that the map from the theta 8 to the Bordism group factors through this group theta 8 S21. And using the result of Fang and Klaus, we know that the map from theta 8 to the Bordism group is surjective onto the torsion, which means that the map from the Z4 also has to go into this image. So we get a commutative diagram, commutative triangle like this, and but since the identity map of Z2 doesn't factor through Z4, the only possibility for this diagram to exist is that the map I has to be trivial. So this is how we get that the Bordism classes of X and X plus sigma have to be equal, and so we can apply the statement of Kreck's surgery theory in this setting and prove that X is diffeomorphic X plus sigma. And I have very little time, so I think I will stop here and don't start talking about the remaining case, but that also uses surgery theory in a similar way to prove that if two complete intersections have the same invariance, then they are bordant, and so they are diffeomorphic. Okay, I will stop here.
Okay, thank you very much. You still have 2 minutes if you, or a few minutes if you want to use them up. But we have for other further questions. So,
Okay.
sorry, do you have more questions, Mark?
Yeah, sure. Yeah, actually, just a basic one. What's omega 8 string of a point?
Sorry?
I'm not used to. I mean, I don't think about string borders very. What's omega 8 string of a point?
Oh, that's just Z plus Z2.
There's a Z plus Z2.
Yes, the Z is the signature, denoted by the signature, and the Z2 is the exotic H sphere.
Is the what? Sorry?
That's the exotic H sphere.
Oh, the exotic H sphere is non-trivial
in string Bordism.
But yet it's, oh, that's weird. But yet it's trivial when you think about it with all this. How does it become trivial when you just by adding a map to CP infinity?
Well, it's not just CP infinity; it's a twisted group. So, well, I didn't define the group properly, but you see in the notation that there's a bundle psi over CP infinity.
Yes.
And so the twisted.
Okay, it doesn't string bound, but then you've somehow twisted the data so that it then does string bound.
Yes, in the twisted group it does.
So the psi is very important for the fact that it's trivial. I was ignoring the psi slightly because I don't quite know what it means, but it's some extra bundle data. What's well, could you just remind me again what the definition of θ8 S2, 1 is?
So it is a diffeomorphism group. Maybe I will give a different definition of θ8 first. So which is the group of homotopy spheres. You can think of that as the group of diffeomorphisms of S7.
Yes.
Which is the boundary of D8. But if instead of D8 we take this non-trivial D6 bundle of S2, and again take its boundary and take its diffeomorphisms, then that's how we get this group θ8 S21.
H star of G is the induced map on homology.
Yes, so to be precise, it's a subgroup of this diffeomorphism group. So I guess you could call this the Torelli group.
Yeah. Cool. Okay.
Okay, thanks. So any other questions? So, well, if not, well, let's thank Csaba again. So thank you for the nice talk, for connecting all the way from Australia. So yeah, and that's then stop here, and hope to see you all next week. So thank you.
Thank you.